times T2 minus theta divided by L2. So we need to make theta the subject according to the question. So just make theta the subject. We can cross multiply and have K1, L2. The cross-section area is the same. We can lose it. I can lose A with this A. All right? So having lost that, we can go ahead and have theta minus temperature T1 is going to be equal to K2 times L1 times T2 minus theta. Eyes open, we need to collect the theta together. So I need your algebra here. That is why we are doing some of, we see in mechanics, there is that algebra we did in momentum, which was a lot. That algebra was training us to deal with algebra in physics. When you go to university, there's what they call mathematical physics. It just prepares you for the advanced proofs in other course units. So we shall have K1, L2, theta minus K1, L2, T1 is equal to K2, L1, T2 minus K2, L1 of theta. When I collect them together, I'll have theta, open brackets, K1, L2, plus K2, L1, close brackets, is going to be equal to K2, L1, T2 plus K1, L2, T1. Therefore, theta can be made the subject. When I make theta the subject, I'll attain K2, L1, T2 plus K1, L2, T1 divided by K1, L2 plus K2, L1. Hashtag proof. Are we okay with that derivation? Do you have any concerns? So today I'm going to add you very many numbers. If I have not, I think they might reach 10. So it's you to do them. But if you don't do them, man, those are your problems. Okay. Now the question goes further and says, also show that the rate of heat transfer. So they're asking us for Q out of T. We have already seen that Q out of T is equal to K1 times cross-sectional area times theta minus T1 out of L1, which was the same as K2 times cross-sectional area of T2 minus theta over L2. So you pick any and substitute their theta. So I'll have the first one is equal to K1 times cross-sectional area times K2 L1 T2 plus K1 L2 T1 divided by K1 L2 plus K2 L1 minus T1, close brackets. All is over L1. Algebra. In the numerator, there is a whole number, there is a fraction. So you cross multiply the denominator and simplify. Will this one fit? No. It can fit the next page. Line K1 cross-sectional area, bracket K2 L1 T2 plus K1 L2 T1 minus K1 L2 T1 minus K2 L1 T1, close brackets, all is divided by K1 L2 plus K2 L1. So far, we're still consistent. Any challenges there? I have cross multiplied this part to go up here so that I have this denominator, and this denominator came and made this L A. Where is our L1? Okay, all is over L1. Now check this one up here. There is K1 L2 T1, same as this one. So if those two are the same, we lose them. So since we have lost them, we shall remain with K1 cross-sectional area times K2 is common, L1 is common, so we shall have K2 L1 brackets T2 minus T1 bracket confirmed divided by L1 brackets K1 L2 plus K2 L1 Vamoosh L1. Now, do you see that this is K1 K2? I can divide the lower part by K1 K2. Space is not enough. Let me use this upper space here. We have already used it. So more algebra there follows, and we shall have the following. The rate of heat transfer will become K1 cross-section area, K2 divided by K1, K2, brackets, T2 minus T1, close brackets, all divided by K1, L2 plus K2, L1 divided by K1, K2 divided by K1, K2. I can lose the K2, I can lose the K1. I can vamoosh these two up here by losing both of them because of division. Finally, I will have the rate of heat transfer as equal to cross-sectional area capital A brackets T2 minus T1 close brackets all divided by L2 out of K2 plus L1 divided by K1. Hashtag our solution. There you go. Unless if someone has a concern that you need to raise. Any concern if I can remove the screen? So I'm assuming you've already screenshotted that. So I wanted to show you some images here just for explanations. That if you have an image like this one, which is showing you that heat can be conducted from a hot environment to a cold environment, one thing you have to have in mind, always remember, as we are winding up this area, you should remember that heat flows from a region of high concentration to a region of low concentration. So that means heat flows from the region of high temperature to a region of low temperature. So if according to that diagram, T2 has a great temperature, then heat flows from T2 heading towards the T1. That is why you see those two arrows of heat flow going towards T1, which is a cold environment, whereas T2, as you can see also that hot environment, shows that the heat is flowing towards the other side. So in that sense, you should be knowing which one is attaining more heat, which one is having less heat. So the conducting solid in this case is assumed to be at a temperature maybe theta, because it is the junction between the two ends which have different what? Temperatures. We can have another interpretation here. Also, this is trying to depict the same. As you can see, this side, which is more red, has, okay, according to this illustration, T1 is greater than the side which has T2. So T2 is at temperature. This side is where we have T2. This is where we have T2. This way, this is where we have T1. So heat is flowing towards this side. So that's why this arrow is showing you that heat is flowing to a region of low concentration or of low temperature. So in that sense also, there's another image which I wanted us to see. This one is an image talking about the equation of rate of heat flow. Yeah, which equation we have been dealing with in this area for quite some good time. So it's an equation which deals with the rate of heat flow. Here is showing you the heat flux as it flows from a region of high concentration to a region of low. So it is flowing from end 2, which has temperature T2, to end 1, which has temperature T1. And T2 is greater than T1. Yeah. Sometimes this is what we call the Fourier's law. Those of you who proceed with physics, you reach in university and cover what we call the Fourier series, which are very good items to deal with in physics. Look at some of these items like I've just showed you. You'll see that if you have items which are in series, yeah, and items which I think there's a question I gave which was having items either in series or in parallel. When they say they are in series, the diagram is like the way I've drawn the last diagram. Yeah? For example, if they tell you a composite block is in series, this is in series. You combine the first one and you combine the what? Second one. This is what is showing you. Whereas in parallel, one is just up and the other one is down. Okay. So when they are in series, the rate of heat flow is the same throughout, in a way that the rate of heat flow through the first one is equal to the rate of heat flow through the second one. Whereas if they are in parallel, you add the rates of heat flows. That's why here we have been adding according to this derivation. So you can be in position to land on numbers which will be predicting series and numbers which will be predicting what? Parallel combinations. So you be very sensitive to know how to go about them. Okay. So this image also is trying to illustrate. The idea, it was trying to have something which is close to the function we have just derived, but it's not actually the same number. That was general. Then this is just an illustration of how heat can flow maybe from the ground to the surface. Maybe heat is flowing from the core, yeah, then it passes through up to the green surface of the earth. These ones are thermalconductivities. The series of them, diamond has the highest thermalconductivity. You know, diamond is not so easy to what? To heat and then melt, or to melt. We know it's one of the hard metals. Yeah. So that is why it has a very high thermalconductivity. Then it is followed by silver, copper, silicon carbide. We have aluminum, graphite, and as you go down, you'll meet other items like krypton, copper, polythene. They all have different thermal conductivity. So not any one material has the same thermal conductivity as the other. That is what that series is trying to tell us. Then let me see if I have another one here. Nowadays, it is very cold. I think you can feel it. I remember mentioning how we can warm up ourselves in bed. When you cover yourself in bed and you don't allow the heat from your body to escape, eventually it is that heat that warms up the bed and you feel warm. Yeah? Not any other heat. One might say, but how do I get heated up in bed? When you cover yourself and your body is emitting heat to the blanket and to the bed or to the mattress, that heat, because the blanket is covered, and that is why they designed bed covers. For bed covers, they have air spaces within them. So the air does not conduct the heat away. So the air acts as insulators, so maintaining the heat within you, between you and the body and the bed cover. The body cover, the body and the bed. So the heat is not escaping anywhere. So at the end of the day, you end up being in position to do what? To keep yourself warm very easily in a bed like that one. This illustration is cylindrical. You've heard of cylindrical illustrations. There's a question I gave, which was saying a cylindrical, was it saying a cylindrical what? There's a question which had a cylindrical something. A cylindrical iron vessel with a base of diameter 15 and a thickness 0.3 has a base count coated with a small film of soot. Yeah, so they can tell you that the base here is coated with soot. Then this soot, maybe if it's a cylinder going into a stove, they subject it to heat here. So the heat here is different from the heat immediately after the soot. It's different from the heat to the saucepan, different from the heat which is within the water, maybe in the saucepan we are trying to boil. So we should be able to interpret all those aspects. And the same illustration has been brought out here. Although this one was mainly talking about Newton's law of cooling, but idea it is predicting the same thing which I've just talked about, that if you provide the heat down this way, and maybe this is soot, the temperature this soot has is different from the temperature the saucepan bottom has. The saucepan bottom here has a different temperature from the soot. Then from the saucepan bottom, you go to the water inside the saucepan. Actually, yeah, you go to water inside the saucepan. All those will be at different temperatures. But because of steady state, the rate of heat flow is the same. You can always predict the temperature of soot. You can predict the temperature of the saucepan. You can predict the temperature of the water. So as you look at those questions, there are various questions I'm going to send, plus those ones I sent last time. Please have those interpretations in mind. Okay. So I think with that, you can stop here. So let me send the numbers and you look at them. Okay, you can have a good day, unless if someone has a question. But let me send the numbers back. If I send more numbers, please try them and send them so that I can take a look at them on your WhatsApp lines.